In Part 2 of Lecture 4, we will introduce lexical analysis. Regular expressions can be processed by finite automata, theoretical machines first postulated by McCulloch and Pitts. It is more practical to use transition diagrams because of features that they have which are different from those in a finite automaton. There are frequently specific actions performed when you reach the final state of an automaton. Transition diagrams allow the user to associate them with final states in a transition diagram. It allows you to back up from a state, which effectively allows you to push a lookahead character back into the input stream. This is necessary because a scanner cannot determine if it has reached the end of a lexeme until it has gone one character too far. Transition diagrams allow you to create classes of characters, such as letters or numbers or others, and so on. This makes the diagram easier to read than it would be otherwise. We use the B and F notation for lexical requirements, where A, vertical line B, means either A or B but not both. AB means A followed by B. AB, all in parentheses, followed by an asterisk, means the string A followed by B 0 or more times, and A, vertical line B, all in parentheses, followed by C, means either A or B with a C afterward. The lexical categories or classes can be described in BNF as you see here. You can declare letter to be any one of 52 characters, a digit to be 0 through 9, and other to include a wide range of punctuation. After we declare these categories, we can use them in specifications for identifiers, integers, real numbers, and other strings commonly found. The transition diagram that you see here shows that we are scanning for either an identifier or a number. The identifier in this language consists of a letter followed by as many letters or numbers as you might want. Similarly, a number consists of 0 or more digits followed by a non-numeric character. As we get ready to write the scanner, there are a few practical concerns that we must address, starting with the lookahead character. Also, some languages are case sensitive and others are not. We will need to skip all the lead blanks and comments before we encounter the first meaningful word. Lastly, we need to be clear on exactly how we are going to use the first character. In many languages, the first character can tell us if the lexeme is an identifier or a number or an operator, some special character. This makes it simpler to scan for the rest of the lexeme. It is virtually impossible in many instances to know that you have read the last character in a word or other lexeme without actually going too far. This leaves us with two options. When we go one character too far, we can push it back into the input stream. An alternative is to replace the lookahead character immediately after using it. By doing this, you avoid the need to push it back into the input stream. If the lookahead does not belong in this lexeme, you don't concatenate it to the lexeme, and you have a character with which you can start scanning for the next lexeme. The scanner described in this and the following slides uses the first approach. The method getTC returns a null byte if the program is already at the end of the file. This will inevitably lead to a token of end of file. If this is not the end of file and the next character is a new line, the line number is incremented. Having the current line number is very useful in error messages. Otherwise, you return the lowercase version of the character, assuming it's a letter. Other characters are simply returned as they are. This allows the language to be case insensitive. If you want, or if you need the scanner to be case sensitive, you simply return the character without converting it to lowercase. ungetTC simply reverses whatever the most recent call to getTC does. If the character is a new line, the line number is decremented to keep the line count accurate. Older programming languages are mostly case insensitive. Fortran and COBOL were originally written exclusively in uppercase, but this had more to do with limited availability of lowercase on older computer systems than a conscious choice. When and where it was available, it was legal for use in both languages. Unix introduced the idea of case sensitivity to save processing time, and the idea was then carried over to C, C++, Perl, Java, and other languages. If a language is case sensitive, there is no real problem. You simply return the character that was read. But if the language is case insensitive, this won't work. Capital A and little a have different ASCII and Unicode values. They are considered different characters. The conversion between upper and lower case is a simple one, and most languages that do even minimal character manipulation have methods for case conversion. We can resolve this problem by converting every letter to one case. In the example below, every character was converted to lower case, although if we decided to use it, uppercase will work as well.